My name is Bryan Gaensler, and I'm an astronomer at the University of Toronto in Toronto, Canada. And really excited to be able to talk to you tonight. I've never done a lecture like this online and YouTube before, but it lets us talk to a whole bunch of people from all around the world. So tonight I'm going to talk to you about the world records of the universe. I'm an astronomer. So I don't know about you, but I get excited whenever anyone sets a world record. A lecture like this. So I remember about, it lets us talk to a whole bunch of people from all around the world. 10 years ago, when Jamaica's Usain Bolt ran an incredible 9.58 seconds. This was the fastest 100 meters that has ever been run. It was so much faster than anyone had ever been run before. And it just blew me away that anybody could run that fast. Like, this was the fastest anyone in the entire history of humanity had ever run. And, you know, this record may never be broken. It just was a marvelous human achievement. Now, I can't run as fast as Usain Bolt, but it's worth putting things into perspective. The fastest speed that Usain Bolt hit during that 100-meter run was 44.6 kilometers an hour. So that's certainly a lot faster than I can run, 44.6 kilometers an hour. But on all things considered, it's not that fast. If you drove a car today, and I admit that right now, many of you didn't drive a car today, but if you last time you're in a car, you probably drove faster than 44 kilometers an hour. Every time you get in a car, you go faster than Usain Bolt. So on the one hand, this is one of the most amazing achievements ever. On the other hand, 44 kilometers, not a big deal. So what I'm saying here is that as amazing as world records are, when you put them in perspective, you realize that what we humans can do is not as amazing as you might think. So Usain Bolt, fastest man ever, 44.6 kilometers an hour. How fast does that compare to objects in space? So let's start with our own planet Earth. How fast is the Earth going? Is the Earth going faster than Usain Bolt? Well, the answer is the Earth is going a lot faster than Usain Bolt. As the Earth orbits the sun every 365 days, it is traveling at 107,000 kilometers an hour. 107,000 kilometers an hour is the speed of the Earth around the sun. So that's something like more than 2,000 times faster than Usain Bolt. But even that is not a very fast speed. The Earth is going around at 107,000 kilometers an hour. Venus and Mercury are going around even faster than that, but those are not the fastest planets out there. We're now in an exciting time in astronomy where we know of thousands of planets going around other stars, and some of those planets are much closer in and much faster than our own Earth or any of the other planets around the sun. So here is one of those fastest planets. This is a planet called WASP-12b. Here it is down here. This is an artist's impression. We can't get photos this good, but this is what it might look like. And it's going around its parent star at 863,000 kilometers an hour. That's something like 8 times faster than the Earth around the sun. Now, it's hard to understand what 800,000 kilometers an hour, what that actually means. So another way of putting it into perspective is it's about 240 kilometers a second. So that means that to get from, say, Toronto to Montreal, it would only take you about 2 or 3 minutes. So it's going really fast, and it takes about 26 hours to go around its parent star once. So while it takes us 365 days to go around our star, WASP-12b is so close to its parent star and moving so fast that it only takes 26 hours. As you can see from this artist's impression, it's so close to its parent star that it's actually being evaporated and is actually melting as it orbits its star. So WASP-12b isn't going to be around forever, but right now it's traveling at 240 kilometers every second. So this is much faster than Usain Bolt. We've now got to a point where we're traveling maybe 200,000 times faster than Usain Bolt, but 20,000 times faster than Usain Bolt. But is this the fastest thing in the universe? Well, not even close. So this is one of the fastest planets we know about. What about the fastest stars? Well, this is an artist's impression of a star with a very poetic name. It's called SDSS JO90745.0 plus 024507. And this is a very unusual star. And this star has actually been kicked out of our Milky Way galaxy. So here is an artist's impression of our home galaxy, the Milky Way, which has hundreds of billions of stars. And this star, rather than just slowly orbiting the Milky Way, actually got booted out of our Milky Way at a very high speed. And it is traveling at 2.5 million kilometers every hour. It got kicked out of our Milky Way about 150 million years ago, and it's rapidly zooming off far, far out into space. Is that the fastest star? Well, no, there are even faster stars out there. So this one is traveling at 2.5 million kilometers an hour. But here's another star with another great name. This is RxJ0822.0 minus 4300. We are just so good at coming up with names in astronomy. And this star, so you can see it here. It's this little white dot here. And if you zoom in, here is it moving. Here is where it was in 1999, and here it was in 2005. And you might not think that motion is very impressive, but at the immense distance to stars like this, this is an incredibly fast motion. We're not used to looking at the sky 6 years later and seeing the stars in new positions. But in this case, we actually can see that the star has moved. How fast is it moving? Well, it is moving at 5.7 million kilometers an hour. That's 50 times the speed of the Earth around the sun. That's 7 times faster than WASP-12b goes around its parent star. And it's twice as fast as the star I showed you in the last slide that got kicked out of its orbit. Another way of putting it is that it only takes 2 seconds for this star to travel the distance from Toronto to Vancouver, or from Los Angeles to New York, or from Sydney to Perth. If you've ever done one of those trips, they normally take about 5 hours. This star can do that trip in 2 seconds. Or another way of putting it is that this particular star can travel the distance from the Earth to the Moon in just 4 minutes. When astronauts went to the Moon in the 1960s and 1970s, it took them about 3 days. This star, it would only take 3 minutes. So is this star the fastest thing in the universe? Well, no, there's even faster things. The fastest individual object that we have ever recorded, and this is a record that's now stood for almost 30 years, is a tiny subatomic particle. And unlike the other objects that all have a name that's just lots of numbers and letters, this particle is known as the oh my God particle, because people could not believe how fast it was traveling. So this subatomic particle crashed into the Earth's atmosphere, a bit like this artist's impression here of particles crashing into the Earth's atmosphere. And it crashed into the Earth's atmosphere at exactly 1:34 a.m. and 16 seconds on Tuesday, the 15th of October, 1991, near the small town of Dugway, Utah in the United States. So if you've been in Dugway in October 1991, looking up at 1:30 in the morning, you would have, if you had really good eyes, seen this little flash of light as this subatomic particle exploded into a shower of sparks. And scientists were able to measure the speed of this particle before it crashed into the Earth's atmosphere. And it was pretty incredible. So let me explain to you how fast this is going. The cosmic speed limit, the fastest that anything in the universe is allowed to travel, is the speed of light. And so light beams travel at a finite speed, and that speed is about 300,000 kilometers every second. So the fastest thing in the universe is light, and no individual object or particle or star can ever travel at or faster than the speed of light. That's completely forbidden. But how fast was this particle traveling? Well, it wasn't traveling at the speed of light because that's forbidden, but it was traveling at 99.99999999999999999999999999999999999% of the speed of light. That's 99.219% of the speed of light. So that's so ridiculously close to the speed of light. So one way of understanding how close to the speed of light this is that suppose that this particle and a beam of light had a race. So we know who's going to win. The light beam is going to win because light travels the fastest. But let me explain to you how close the race would be. Suppose they raced for 1,000,000 years. So this particle and the light beam had a race for 1,000,000 years. The light would win, but how much would the light win by? It would win by about 4 centimeters. So even after 1,000,000 years, this proton would only, this subatomic particle or proton or something, would only fall behind the beam of light by 4 centimeters in 1,000,000 years. And that is the fastest particle the fastest object we have ever recorded in the universe. And it's a record that has stood for almost 30 years, since 1991. And it's really going to take some beating. So as amazed as we were by the world records here on Earth of someone like Usain Bolt running 100 meters in 9.58 seconds, you can see that there are things out there in the universe that are much, much, much faster than Usain Bolt or anything else here on Earth. So I started by telling you about the fastest things in the universe. Now I want to focus on temperature, and I want to talk to you about the coldest thing in the universe. So if you ask an astronomer, what's the coldest thing in the universe? Most astronomers will say to you, I know, this is an easy question. You're trying to trick me, but everyone knows the answer to that. The coldest thing in the universe is something called the cosmic microwave background. Now, this is a glow left over from the beginning of the universe almost 14 billion years ago. So we know that the universe began in something called the Big Bang, sort of like a big explosion, almost 14 billion years ago. And the incredibly intense glow from shortly after the Big Bang still exists. And you can see it coming from every direction in the sky at once. But because the Big Bang happened almost 14 billion years ago, that glow has cooled down in temperature enormously. And we can measure, this is what it looks like if you could see the whole sky with very powerful eyes. You could see this faint glow from the whole sky. And the temperature of this glow is minus 270.42 degrees Celsius. We've measured it very precisely, minus 270.42 degrees Celsius, which is just 2.73 degrees above absolute zero. And so most astronomers would say that outside labs, inside people's labs, we can make it even colder than this. But outside people's labs, many people would say this is the coldest thing in the universe. For those astronomers who said that that's easy, we all know the answer to that would actually be wrong. Because there's actually one place in the universe that naturally is even colder than the cosmic microwave background. And that's this beautiful glowing nebula called the Boomerang Nebula. Now, as you can probably tell from my accent, I'm Australian. So, you know, I've seen a lot of boomerangs in my life, and I do not know why this is called the Boomerang Nebula. It looks nothing like any boomerang that I've seen, but this is the Boomerang Nebula. And it's very pretty. It's this glowing cloud of gas from a dying star. And when people measured its temperature, they got a bit of a surprise, because the temperature of the gas in the Boomerang Nebula is actually minus 272 degrees Celsius, which is a couple of degrees even colder than the cosmic microwave background. The gas in the Boomerang Nebula is only 1 degree above absolute zero. So it's even colder than the rest of the universe. If you were standing inside this Boomerang Nebula, you could actually perhaps warm yourself up by holding your hands up to the sky, because the glow from the universe is actually slightly warmer than this nebula. So you might be asking, well, how could this nebula get so cold? And the answer is it's a bit like a refrigerator. If you ever thought about how a refrigerator works, a refrigerator cools things down by having gas inside the refrigerator rapidly expand. And if you look at the Boomerang Nebula, you can see the same thing that's happening here. The star is in the center, and the gas is flowing up here and down here. And you can see from the shape of the glow that this gas is rapidly expanding. And so it's that rapid expansion which cools down the gas and cools it down so it's even colder than the rest of the universe. So as far as we know, this record might be broken in the future, but this is the coldest thing we know of in the universe. It's minus 272 degrees Celsius, just 1 degree above absolute zero. So let's move on to another record. Now let's talk about the biggest things in the universe. So planet Earth is pretty big. If you've ever flown from one side of the world to the other, it takes a really long time. When I live in Toronto, but my hometown is Sydney, Australia. whenever I go home, it takes about 24 hours to fly from Toronto to Sydney. So that's a really long trip. And that's because the Earth is a pretty big place. The Earth is more or less a sphere. And to go from one side of the Earth to the other is about 12,700 kilometers. So the Earth is really big. 12,700 kilometers is an enormous object. But as you know, by astronomical standards, the Earth is relatively small. There are many things in the sky that are much bigger than the Earth. The obvious one is the sun. Our sun is a pretty ordinary star, and it's huge. Our sun is 1.4 million kilometers across. You could fit roughly 100 Earths from one side of the sun to the other. So when you see a beautiful big loop like this big explosion of gas on the sun, to give you a sense of how big that is, you could fit the Earth inside this loop about 4 times. So you can probably see hopefully see my green spot. That green spot is roughly the size of the Earth relative to the sun. So the Earth's pretty big, but the sun is much, much bigger. But even the sun is not that big. The sun is a pretty ordinary stars, and there are some stars that are much, much bigger than the sun. So here's one of them. This is a star called Mira. The star itself is buried in this cloud of gas up here, and it's huge. Mira is 500 million kilometers across. It's about 400 times larger than the sun. So one way of thinking about that is if you put Mira where the sun is, it would be so big that the orbits of Mercury and Venus and Earth and Mars would all fit inside Mira. And that's pretty amazing, but it's also pretty intense because Mira is simply an older version of the sun. If you wait for the sun to get 4 or 5 billion years older, it will basically turn into a star like Mira. It will be 400 times larger than it is now, and it will swell up and envelop all the inner planets, including the Earth. The other wonderful thing about Mira is, as you can see from this picture, is that it's actually leaking. Mira is traveling across the sky pretty fast. It's moving at about 500,000 kilometers an hour. And as it zooms across the sky from left to right, it leaves this leaking trail of gas behind it. It's leaking about 20 trillion tons a second of gas. And this leaky trail extends over the sky by 13 light years. So even at the speed of light, it would take you 13 years to travel from one end of this trail to the other. We can't see this trail with our naked eye, it's too faint, but if you could see it, it would stretch across about 4 times the diameter of the full moon. So Mira is this enormous dying leaky star. It's 400 times bigger than the sun. And of course, the sun in turn is 100 times bigger than the Earth. But even Mira isn't one of the biggest stars. One of the biggest stars we know of is Betelgeuse. Betelgeuse is a naked eye star. It's an orange star in the constellation of Orion. And it's 1.6 billion kilometers across. So Betelgeuse is about 1,000 times larger than the sun. Another way of thinking about it is that if Betelgeuse were the size of a basketball, so about this big, then the sun would be the size of a dust mite, and the Earth would be the size of a bacterium. So Betelgeuse is really, really big. But that's an unbelievably big star, but there's even bigger objects out there. Of course, Betelgeuse and the sun are just 2 stars in our galaxy, the Milky Way galaxy. Our galaxy, which probably looks something like this, it's hard to tell from the inside, but we think it looks something like this. Our galaxy is 100,000 light years across. So even if you could travel at the speed of light, 300,000 kilometers every second, it would take you 100,000 years to cross from one side of the Milky Way galaxy to the other. If you want to know that in kilometers, it's about 1,000,000 trillion kilometers, or 1 with 18 zeros at the end of it. So the Milky Way is much, much bigger than even mighty Betelgeuse. Is the Milky Way a big object? Well, not really. It's a pretty ordinary galaxy. There are much bigger galaxies than the Milky Way. And the biggest galaxy we know of in the universe is this galaxy here. It's called IC 1101. And it is 5 million light years across. That's 50 times the size of the Milky Way. So a Milky Way, as big as it is, you could fit the Milky Way across this galaxy 50 times. And this galaxy IC 1101 contains trillions of stars. So if you took the biggest star we know of, something like Betelgeuse, and shrink it down to the size of a pinhead, then the Milky Way would be 300 kilometers across, but IC 1101 would be the size of planet Earth. So these things are unimaginably large. But is IC 1101 one of the biggest things in the universe? Well, not even close. There are even bigger things. So it turns out that galaxies aren't all separate, but they all sort of cling together in big, long chains and walls and sheets. So what you're seeing here now is a map of hundreds of thousands of galaxies. So each blue dot is the location of a galaxy somewhere in the universe. And what you can see is that the galaxies aren't just randomly spread like grains of sand, but they're clumped into this foamy filamentary pattern. And what astronomers discovered is that some of these patterns are enormous. So what you can see circled here is this huge chain of galaxies all joined together. This is known as the Sloan Great Wall. And this chain of galaxies is 1.4 billion light years across. So again, even if you could somehow travel at the speed of light, 300 kilometers a second, it would take you 1.4 billion years to travel from one side of the Sloan Great Wall to the other. The Sloan Great Wall is enormous. It stretches across a quarter of the sky. You'd think that a giant of galaxies that stretches across the quarter of the sky would be pretty obvious. But amazingly, the Sloan Great Wall was only discovered in 2003, only 17 years ago. And since then, astronomers have discovered other chains of galaxies like this, which might be even bigger. So the last thing I want to talk about, that I want to spend a bit of time talking about, is what about sound in space? What are like the loudest things in the universe? And the first thing you might be thinking is, well, hang on, there is no sound in space. I mean, I'm happy with world records about speed and temperature and size, but sound isn't something that really comes up in astronomy. So let's talk a little bit about sound in space. So I'm going to show you 2 video clips from 2 famous science fiction movies, and they treat sound in space in very different ways. Once you watch, what I want you to do is I want you to watch each of these clips and think about which one got it right and which one got it wrong. And then we're going to talk about what actually is going on. So here's the first clip. Hopefully you'll recognize it. It's from a very famous movie. So here we go. Okay, so hopefully most of you recognize the movie. That was Star Wars 4, A New Hope. And in that movie, there's lots of sound in space. There's rumbling of spaceships and lasers and explosions and all the rest of it. So now I'm going to show you a very different movie. This movie came out, I think, 8 years before Star Wars. Another very famous movie. And let's look at how they deal with sound in space. So here we go. So I love this movie. I love both those movies. The second one you saw was the movie 2001: Space Odyssey. And that was a movie that's very different from Star Wars, and it tried to get a lot of the science right. And what you could see is that what happened was as the astronaut went into a vacuum and all the sound completely disappeared and everything is completely silent. And it was only once he started to let air back in that the sound came back. And so most people would say that the first movie, Star Wars, got it completely wrong. And the second movie, 2001: A Space Odyssey, got it completely right, because sound needs a medium in which to travel. And so if you have air, you can hear sound. And if you have no air, you can't hear sound. So there's sound here on Earth, and there is no sound in space. So most people would agree that Star Wars got it completely wrong. You can't hear lasers and explosions in space. And most people would say that 2001: A Space Odyssey got it right, in that in space, it's a vacuum and everything is completely quiet. But the right answer is somewhere in the middle. As we said, you need a medium to hear sound in space. Sorry, in general, anywhere, you need a medium to hear sound. When a speaker plays music, the individual air molecules vibrate back and forth. The molecules aren't traveling from the speaker to you, but they vibrate back and forth, and that vibration gets transmitted through to your ear, and you hear it as sound. So in order to hear a sound, you need vibrating particles between the object making the sound and your ear. And everyone knows there is no sound, there is no particles in space, so you can't hear sound. And there are other movies that have played on this. This is another movie from 40 years ago or so, a movie called Alien. And the whole slogan of the movie, a very famous slogan, was, "In space, no one can hear you scream." The idea being that in a vacuum, you can scream as much as you want in space and no one can hear you. But all of these arguments that in space there is no sound assume that space is a vacuum. If there was some gas in space, you might say, well, okay, if there was gas in space, then maybe you could make sounds. But of course there is gas in space. You all love pretty pictures of space. And here is one. Here is the Orion Nebula. Here is gas in space. Space is full of gas. And so as long as you have gas in space, you should be able to have sound in space. So there are sounds in space, and it's worth talking about what sort of sounds are actually there. So one particular important sound that happens in space is the sound of a sonic boom. So a sonic boom is a tremendous crack that you get when an object breaks the sound barrier. So here on Earth, the sound barrier is about 330 meters a second, or about 1,200 kilometers an hour. And when an object, like a plane, travels at more than 1,200 kilometers an hour, you get this tremendous boom as it breaks the sound barrier. And so here's an actual photograph of a plane breaking the sound barrier. So the gas in space also has a speed of sound. It's not that different from the speed of sound here on Earth. It's about 30 times faster. So it's faster, but not by a huge amount. And if you have any object that travels faster than the speed of sound in the gas in space, you get a tremendous sonic boom. And there are objects that travel faster than the speed of sound in space. The most familiar one of them is when some stars end their lives, they detonate in a colossal explosion called a supernova. So here's an actual photograph of a supernova. This is one from February of 1987. So right here is a star about to die. And if you had looked up the next day in February of 1987, that star actually blew up. Now we here on Earth didn't hear any sound, so you would not have heard that. But if you were near the star, then the debris of the star exploding raced out at about 10% of the speed of light, about 100 million kilometers an hour. Now the speed of sound in all of that gas is about 36,000 kilometers an hour. So the speed of sound was 36,000 kilometers an hour. This explosion is moving outwards at 100 million kilometers an hour. It was going much faster than the speed of sound. And so it broke the sound barrier. And if you were near this, you would have heard an unbelievably loud sonic boom, one of the loudest explosions in the universe. So you have to be right near the explosion for that to actually happen. But it turns out that these explosions last for a very long time. And I can prove this to you because in the year 1604, in the month of October, a famous scientist called Johannes Kepler wrote a book called De Stella Nova, which is Latin for about the new star. So they didn't have Netflix or Amazon or anything back then. So, there wasn't a lot to do. So when someone wrote a book saying, I found a new star, people were actually excited about it. It was quite a big deal. The other reason why this was a big deal is because this new star, and here is a map showing you its location in the constellation of the Fucus. This star was so bright that you could see it with your naked eye in broad daylight. So we're not used to seeing stars besides the sun in daylight, but this explosion was so bright that you could see it in broad daylight for a few weeks in October of 1604. If we look at it with our telescopes at that exact position right now, 416 years later, we can still see the debris from the explosion. So the explosion was somewhere about here, and 400 years later, we can still see all of the aftermath of the explosion moving outwards, and that shockwave is still moving outwards. So if you were an astronaut floating out in space and this shockwave overran you, you would experience the loudest sound in the universe. Well, how loud? Well, we measure sounds in decibels, and my voice on your computer right now might be about 50 or 60 decibels, depending on how loud you've got your volume. A really loud sound might be 100 decibels. Going to a rock concert so loud that your ears hurt might be 120 or 140 decibels. The sound of this shockwave running over you would be 330 decibels. So that's about 1 billion times louder than the loudest sound your ears can safely withstand. So not only is it wrong to say there's no sound in space, it's actually the opposite. The loudest sounds ever conceived are actually sounds in space. 330 decibels is the loudest sound in the universe. But what else? What are some of the other sounds in space? Well, it turns out there are some very deep notes in space, much deeper than the human ear can hear, and much deeper than any sounds on Earth. So what you're seeing on the left-hand side here is a picture of the hot gas from a giant cloud of dozens of galaxies called the Perseus cluster. And it's a very distant object. It's about 250 million light years away from Earth, but we have powerful telescopes and we can make pictures of it. And if you look at the picture on the left, you can see that the hot gas in the galaxy is not completely smooth, but it's broken up into lots of different ripples. And those ripples are actually the signature of a sound wave rippling outwards from the center of this hot cluster of gas out towards the edge. And even though we can't hear the sound wave thrumming through this cluster, we can work out, based on the spacing of the ripples, what note this whole cluster is playing. And we can calculate it quite precisely. And amazingly, this whole cluster is vibrating with the note of a B flat. But it's not a B flat that you might imagine. It's a very deep note. How deep is it? Well, it's 56 octaves below middle C. Or to put another way, it's 6,000 trillion times deeper note than the lowest note the human ear can hear. Or to put it another way, if you wanted to play this note, you would have to add another 635 keys to the left-hand end of your keyboard to play this note, arguably the deepest note in the entire universe. This B flat, 635 keys off the end of the piano. This note is pretty loud. It's not as loud as the one we just talked about, but it's about 70 decibels, so perhaps about as loud as my voice is to you right now. How is this note being made? Well, there is a giant black hole shooting out hot gas at the center of this cluster, and the right-hand side is showing you a computer simulation of how this cluster might have been made. And one way of thinking of this is if you have a bucket and you want to fill that bucket with water, you can hold the hose up higher up here, and you can slowly fill the bucket with water, or you can turn the hose on really, really strong, and you can push the hose down against the bottom of the bucket. And if you push the hose down against the bottom of the bucket, you know that you hear this deep note, and the whole bucket fills up with frothing water. And that's exactly what's happening here. The black hole is shooting out material, and it's running into all the stuff around it and frothing up and creating this note of a B flat. Now, as I said, this B flat is only 70 decibels, but what's really remarkable about this is that while the explosion from a supernova is 330 decibels, that's just a one-off crash. That's just a big bang like that, and it's over. But this is a sustained note. This B flat has been held for 2 billion years so far and has not shown any signs of being given up. So I'm sure, if you've ever gone to an opera and you're impressed when someone, goes, la, and holds a note for a really long time and everyone claps. Well, this black hole has been holding this B flat note for 2 billion years and is not showing any sign anytime soon of needing to take a breath. The energy needed to hold this note across this giant cloud of gas is staggering. The energy you need every second to hold this B flat is a factor of trillion times larger than the combined output of every power station combined on the planet Earth. So that's just mind-boggling, just how much energy you need to sustain this really loud note. What about the first note in the universe? This is the last thing I'm going to talk about tonight, which is what was the very first note in the universe? So here is an entire history of the universe. It's pretty amazing that we can show the entire history of the universe just on one slide, but here is the whole history of the universe, starting at the beginning at the Big Bang, and going through time all the way through to the present time, 13.8 billion years after the Big Bang. So you might think the first sound in the universe was the Big Bang. After all, the word bang makes it sound like it was pretty loud. But the Big Bang itself, despite its name, was actually completely silent. But what happened in this period up here, with this sort of reddy orange period, is that as the universe expanded and cooled, the gas in the universe began to slosh back and forth, like the waves in an organ pipe that go up and down the organ pipe and make the notes. So, and that's what made the first notes in the universe, that gas sloshing back and forth over the first 300,000 or so years of the universe. So initially, this cosmic choir was just sopranos. You can think of the universe, the whole universe, as an organ pipe. And initially, the universe is very small, and so it can only play very high notes. But as the universe got older, the universe got bigger, and it took longer and longer for the gas to slosh back and forth, and deeper and deeper notes got added to the chorus. So 10 years after the Big Bang, the dominant note in the entire universe was an F sharp, but 35 octaves lower than the lowest note that a human ear can hear. And it was a volume of about 90 decibels, so sort of standing near a lawnmower. Over the next 100,000 years, 13 more octaves of even deeper notes were added to this giant cosmic pipe organ, and the volume got louder by a factor of 20. So incredibly, by making measurements of the behavior of the early universe, we can construct the very first sounds in the universe. We can construct the noises the universe was making over its first 380,000 years. Now, I'm pretty sure most of you don't have 380,000 years, so I'm going to speed it up a bit. And I'm also going to raise the pitch by 35 or so octaves so you can actually hear it. But this is a calculation done by an astronomer named Mark Whittle. And here is a greatly sped up, greatly raised up version of what the universe sounded like over the first 300,000 years. But this is incredibly scientifically accurate, except for the fact that the sound has been altered so that you can actually hear it. So here we go. Pretty amazing. I'll play that one more time, but you can hear that note getting deeper and deeper at the beginning as the universe expands, essentially as the pipes get longer and longer. So here, I'm going to play it one more time for you. So that is what the first 300,000 years of the universe's history sounded like. We weren't there. We didn't have a recording, we can't play back, but we can calculate based on the evolution of the universe. That's what it must have sounded like to produce the universe that we see today. So how do we know this? We know this because that sound was being played for the first 380,000 years. But after 380,000 years, the universe, which until then was this big foggy soup of glowing gas, at that point, the universe cleared and cooled down. And the gas stopped sloshing and the universe suddenly went quiet. And what happens is that we can see the exact patterns of gas. This glow that I showed you before from the whole universe is actually the blotchy blue and red colors you can see there is the exact patterns of gas in this giant cosmic pipe organ frozen into place at the moment that the universe cooled down. So I don't know about you, but growing up as a kid in Australia, we used to play a game at birthday parties called Murder in the Dark. And the idea is that you all had to creep around in a room of the house that was completely dark, and you could do whatever you want. But then when someone turned the lights on, you all had to freeze in place, and you'd be having a silly expression in your face or doing something, and you all had to stand in place. And looking at the cosmic microwave background, essentially we're playing Murder in the Dark. All the gas was swirling around and making all this complex, beautiful music. But then 380,000 years after the Big Bang, the lights came on and all the gas froze in place, and it's been frozen in place ever after. So the note that was being played at that exact moment that the lights turned on, we can work it out. The exact note being played at that moment was C, but 54 octaves below middle C, at about 120 decibels, so about the volume of a really loud rock concert. So it's not as deep as the note being sung by that black hole in Perseus. And it's not as loud as a supernova, but it's still pretty remarkable. To play this middle C, 54 octaves, sorry, this note C, 54 octaves below middle C, you would have to build an organ that had a pipe 10 trillion kilometers long. So when we look at the cosmic microwave background, we're actually seeing the note played by this organ pipe almost 14 billion years ago. So what's happened to the whole universe ever since then? Well, the universe, even though the things in the universe have been making sounds, things like giant hot clouds of gas and supernovae, the universe itself has actually been completely silent for most of the last 14 billion years. So the way that I like to think about this, to finish my talk, is that it's a bit like a classical music concert. And if you go to the concert after the concert is over, and in this case, we've turned up way too late, the concert finished almost 14 billion years ago, the conductor and the musicians have left the cosmic stage, and they took their instruments with them. But what happened is that they left behind on the stage, they left behind their sheet music. And by looking with very, very powerful telescopes at this glow from the beginning of the universe, we can actually see the sheet music. And we can not hear the music, but work out what they must have played and reconstruct the music of the beginning of the universe, music that was never meant to be heard, but we can hear it. I hope you think that the universe is as amazing, incredible, and spectacular as I do. Thank you so much for listening tonight. Thank you. So we now have time for a few questions. So we have Cara and Megan monitoring YouTube, and they're going to post some questions that I'll try and answer. So first question doesn't say who it's from, but the question was, can galaxies be considered true objects? So absolutely, a galaxy is a true object. All the stars in the galaxy are held together by gravity. A galaxy is a true object in the same way a person's a true object. A person is just a bunch of separate atoms held together by electromagnetic attraction. You might say a person's not really an object, it's just a bunch of atoms close together. A galaxy is the same, but we're now talking about stars. So a galaxy is indeed a single object. It's a bunch of stars held together in the same way that you or I are a bunch of atoms held together. The next question I've got is about the Sloan Great Wall. And the question was about whether the Sloan Great Wall shows us where the Big Bang is. And I think that question was answered in the comments. And so the question, the second question was asked is, what's going on as you move? So the Earth is actually here, this is us. And as you move further out, it looks like the galaxies get less and less dense. So is that actually real? Are galaxies getting less and less dense as you go farther and farther away? And the answer is no, it's just an effect of the limitations of our telescope. But as you get farther away, galaxies get harder and harder to see. And so these measurements of these very distant galaxies are not as high quality as the data we have nice and close in. And so these data are not quite as useful, and you can't really see what's going on. This set of measurements was made in 2001. We now have much better surveys, and they go much, much further out, way off the edge of our slides now. Are there any other questions out there? So I've got a question from Tracy. Do all black holes make the same noise, or does it depend on size? And so that's a great question. And the answer is absolutely, it depends on size. Generally speaking, the bigger, just like everything with musical instruments, you know that big musical instruments play deeper notes than than small musical instruments, and it's more or less the same with black holes. Big black holes will produce very deep, loud notes, and small black holes will produce higher, quieter notes. It's all relative, of course. Even the notes produced by the small black holes will still be many, many octaves off the left-hand edge of a piano, but the bigger the black hole, the deeper the note. Any other questions out there? Last chance? So Adam's got a good question. Adam says that he's 12 and he wants to know my favorite movie about space. That is a hard one. There are so many great movies about space. So I'm gonna have to think about that. Probably my favorite one is a movie called Contact. It's a movie from about 20 years ago. And it's a movie where an astronomer, not that different from what I do, detects a signal from aliens and actually makes contact with them. And although we don't really know if aliens exist right now, what this movie does is it asks the question, what would it really be like if we contacted aliens? And it wouldn't be a flying saucer landing with monsters with green tentacles coming out. This movie Contact actually talks about what it would really be like to contact aliens. So if you ever wondered what that might be like, I really highly recommend seeing the movie Contact. So we got a question from Ransky. Why is a galaxy considered an object but not a local group? They are both gravitationally bound. So a local group is considered an object. So galaxies are in groups and they're in clusters. And clusters like this one you're seeing here are also indeed single objects. They are held together by gravity. And so the largest gravitationally bound objects we know of are clusters. So I was cheating a little bit here with the Great Wall. The Great Wall is not strictly speaking a gravitational object, and all these galaxies are not being held together by gravity. So the biggest objects in the universe are these clusters of galaxies, and this is even bigger than that. But they are all strung together in a non-random fashion in this big, long chain. Any last questions? We'll take one more. Kara's typing something. We're going to see a question that Kara's bringing in a moment. So question from Jessica's mum. The cosmic microwave background is the whole universe. They think there's nothing beyond that. So this is tricky. This is a tricky question to answer because the cosmic microwave background isn't, we're looking back in time here. So it's the edge of the universe in the sense that we're looking back towards the beginning. The universe, as we know it, we don't know if the universe has an edge. Remember that light from distant objects takes time to get to us. And the universe has only been around for 14 billion years. So if there's an object, that's 20 billion light years away, then the light from that object hasn't had time to get to us yet. So we actually can't see the whole universe, and we don't know how big the universe is. We can only see that part of the universe that's had time to get to us. But the cosmic microwave background is the edge of the universe, only in the sense of the opening credits, so the beginning of the movie. It's looking back in time. We can't look forward in time, but we can look back in time to the beginning. So this glow is our past. It's not. It's the glow coming from the whole universe, 13 billion light years away. Okay, and I'll take one more question from Murdoch. Do you think there's another galaxy with a planet like ours with beings like us? That's a question from Jack. So probably not exactly like us, but there are 400 billion stars just in our galaxy. And there are billions and trillions of galaxies out there. So there are probably many, many planets, and some of them somewhere out there probably have life, and some of that life is intelligent. But I don't think there's any life that's exactly like us. I think we're unique, and our Earth is unique. But perhaps somewhere out there is life that is intelligent and has the same values as us or the same interests as us, and maybe we can talk to them. Okay, so we've got one last question from Asha, which is if superposition means that the multiverse is true, does that mean we can travel to those universes? So at the moment, we don't know of any way to travel to other universes. It's possible that there are lots of other universes like ours all stacked together like a deck of cards. We might see signatures of some of those universes bumping into each other in maps of the cosmic microwave background. If these two universes are very close to each other, it might have affected the sloshing of this gas and we might be able to see it. And there's people arguing about that. So there might be hints in ways in which two universes that are next to each other can actually influence each other. But we don't know of any way actually between universes. Great question calling in tonight. We've got lots more coming up from the Dunlap Institute. We have school lessons at 4 o'clock Eastern, 2 o'clock Eastern every day. We have a picture's worth of 1,000-word talks some days at 4 o'clock. And then a couple of days a week, we have these public lectures at 7 o'clock Eastern time. So check out our website and our social media for more details. And thank you for sharing our excitement and love of the night sky. Stay safe out there, everybody, and I'll see you next time.